Ladies and gentlemen, it is 4/27/2024, and can you believe it? It's Saturday once again. Amazing. And dare I say, Mac, you'll love to see it. I don't even know if you guys can hear me. So anyway, let's get this stream up on the fucking thing. Let's go. Cool. Thought you wouldn't see me again, did you? If only you were so lucky. Here I am. On a beautiful spring day. We're here doing game dev. Can you believe? Whoa. Why is that so big? What the fuck? You got in. We gotta fucking adjust that size. Give me a second. Only I knew how to do that. There we go. Jesus Christ. Oh my god, it's so big. There we go. That's a bit more modest.
GPU instancing is a powerful rendering
We'll turn the desktop volume up because it was a bit soft last time. Couldn't really hear the video for you guys, so we'll turn that to like maybe 7 decibels.
How does it work?
Amazing.
Normally, when you are instantiating some objects, you are doing it one by one.
Let me know if that's too loud or too soft, and I will adjust.
Which is being
or don't. I'm not your mom,
CPU.
but I could
So
be.
the CPU is telling to the GPU
You never know.
it should render some object just once. Then the GPU waits for some time until it receives more information about what the next object to
So
render
actually, today's going to be a bit more of a code-heavy day.
It's a lot slower than GPU.
Once
GPU
I adjust
it's like hundreds
these
of
things.
small CPUs. So what we
Like the
can
height
do
of these,
instead
first of all.
is to send a bunch of information from the CPU to the GPU at one time about all of the objects that it will spawn. And when should you use GPU instancing? It can be pretty useful when rendering large crowds of people, particle
so I'm
effects,
actually going to
water
put these on to contribute to global illumination. It's going to add a bit to the light map size, but I feel like it's kind of necessary to make it look good. So
instancing is done on a simple example of many cubes.
Oh.
So we have empty script on an empty object, and in the script, how do we actually instantiate something using GPU? We can just type graphics.draw mesh instance.
This isn't even a platform. This is a fence. What is this one here?
To supply mesh, the sub-mesh index, which is just if you have multiple meshes into one mesh, you can just choose which one you want to render. Then we need to supply a material and array of all of the matrices. You can think of a matrix just as a transform. It is just holding the scale, rotation and position. And when you are instantiating the meshes, you could do it just in start, but they would disappear, because when you want to be able to see them, you need to be rendering.
Actually, I never looked in here yet. See how the lighting is in here.
I will define
probably sucks.
variables.
Ooh, that's dark. That's hella dark. Goddamn.
I will be instantiating
yeah, boost that a bit.
in a grid,
Like
so I need to know what should
7
be the size
and
of
then the range is like
then
40.
we have the variable for the mesh, material, and array for
then when we bake that, hopefully it'll be a bit better.
Go through all of the X, Y, and Z positions. Just create.
Okay, let's duplicate them. Let's put some on the other side.
Array.
Get this
and
place
then we will just
glowing.
draw instances of all of the objects that we want based on the count of the matrices that we have.
There we go. We'll pretend like there's a light prop there or something. I don't really need to put one.
Because we want to be able
it's not
to
too
see
important.
cubes all the time. First, I'm just initializing the matrices array. So the size of it is just size multiplied by size multiplied by size. Then I'm
should I bake the light maps on these bad boys?
I also have a
it's gonna really increase
so that I know to which index in the matrix
light map bake time, but maybe
matrix.
it did look pretty good.
And
so
then we'll just create it. So we'll use the function matrix 4x4
for now.
.trs, which you can see that creates a translation, rotation, and scaling matrix. So we'll be able to easily input all of the values into it. And it is that simple. So to the position, I'm just inputting x times 2 because I don't want the cubes to be too close to each other. Then we have the same thing.
So yeah, I
While
did
smooth
mention that there's
is
going to be a
I'm
bit
just adding sine of
codey,
time, so
rather
graphing
than
up and down.
3D arty.
And the rotation is just quaternion.identity.
I'm already not
and
watching
the
this video,
scale is
so
just
I'm just going to turn that off. But I was watching this video, which I just remembered because I just saw it was open.
And yield return new wait until delays until the specified condition is true. This is a great way to avoid a lot of messy timers with time.delta time. You can start a coroutine by calling start coroutine and passing in the function name as a string. If you want to call a function after a certain one-time time delay, then it may be easier to use the invoke method. Basically, you can call this and pass in your function name as a string parameter along with a time in seconds. This will call your method after the specified delay. You can also use invoke repeating, which will call a method repeatedly at certain time intervals. I don't need the bots in my game to calculate a new destination every frame, so I use invoke repeating to update their path every half a second instead. Structs are kind of like a light version of classes. A key difference between structs and classes is that a struct is a value type, while classes are reference types. In this way, structs behave similar to primitives. Every time you assign a struct to a variable, that struct is copied. You should use a struct to store immutable data types that logically represent only a single value. A lot of the time, I use a struct when I want to have a list of some custom data type show up in the inspector. For example, I have a struct defined in my player UI manager, which represents a UI group. If I mark this struct as serializable, then I can set the fields of each UI group in the inspector. I also use a struct to store and transmit input for the current frame, since only the input handler class should be able to change the input. Now we're getting to the good stuff. A singleton is a type of class which only allows one instance of itself to ever be created. To implement a singleton, make a static variable of the same type as the class. Then, in the awake method, store the new instance into the static variable or destroy the script if the instance has already been assigned. If you don't know what static variables are, they are variables that belong to the whole class instead of just one object. This means that you can access static members from anywhere with just the class name. Hey, that's pretty convenient. The issue is, non-static members cannot be used in static functions. A singleton gives us the best of both worlds. If you use the static instance variable to reference the actual instance of the script in the scene, then you can access all the non-static members as if they were static. Singletons are most suited for scripts that need to exist within the Unity scene, but also need to be referenced by many different scripts. And remember, there can only be one instance of the script in the scene at a time, so don't try to use a singleton for your enemy script, since there will likely be many enemies in your scene at one time. I use singletons for my manager scripts like my game manager and network manager. I also use it for utilities like my object pool. The object pool needs to be in the scene, but I also want to be able to reference it from anywhere. As part of this tip, I'm going to suggest that you create a manager class anytime you have a bunch of different scripts that need to access a set of information. For example, the current game state and the list of players on each team is important for many different scripts. So that's why I created a singleton game manager class to handle these systems and expose the information to anyone who needs it. Just remember that these managers should still only have one job each and should not be trying to handle too much at once. In game development, much of our code is event-driven. This means most of the time we're just sitting around waiting for something to happen. C# events are well suited for this type of programming, and they can help remove dependency between systems. In my game, the player movement script and the grenade script need to know when the match begins in order to reset their respective action cooldowns, but the game manager handles the start of the match. How should I solve this problem? Well, I could loop through every player in the match, and then get a reference to the player movement and throw grenade script, and then call a public function reset cooldown on each. This would work, but it makes my manager script dependent on the player scripts, meaning I can't change my player scripts without changing the manager script. Let's use C# events to solve this problem. First, I'll make a variable of type action inside the game manager called GameStarted. To trigger this event, I'll call .invoke on that action variable. I use a question mark before the dot operator to avoid null reference exceptions. You can also add parameters like this, but I don't need parameters in this case. Now, my player script can subscribe to this event by referencing the action variable and then using += to link its own function to that event. Now, when the game started event is invoked by the game manager, all the scripts which have hooked into this action will be notified. This means that the game manager does not have to deal with my player scripts at all. And best of all, if another script needs to reference this event in the future, then I won't have to change my game manager to include it. In general, it's okay if your scripts depend on your manager classes, but not the other way around. I also use C# events for my health class. I have an event for when the health is changed and for when the object has died. This allows me to separate the health and regen logic from stuff like UI and death logic, which is handled in a different script.
Let's connect some of the props.
Now I can use health as a component that can be reused and added to any object.
Too big.
Unity has its own event system, which you may prefer. It works in almost the same way as a C# event, except you define a Unity event variable instead of an action variable. The main advantage of Unity events is you can assign subscribers in the inspector just like you would for button events. In my game, I've used C# events instead because I prefer to link things up in code. In my game, I wanted to code a system that allowed me to animate menu screens. So I made an animation controller which has a play enter and play exit coroutine. Then inside these coroutines, I loop through all the elements in the animation, get the component UI slide in anim, and then call play on that script. That works fine, but what if I want to play a different type of animation? Well, I could use one script that has the logic for every animation, but then I'd need a bunch of if statements inside the play function, and things could get very messy very quickly, depending on how different the animations are. It turns out that this problem can be easily solved with an interface. Interfaces can be used when you want two classes to behave similarly without enforcing a relationship between the classes. The structure of an interface is similar to that of a normal class, except you don't need a constructor and you don't actually provide the implementation for any methods. When another class implements an interface, they are required to provide the implementations. In this way, an interface represents a contract that guarantees certain methods will exist in a class. So how about I make an interface called IUI animation, which has the method headers play enter and play exit. And I'll make the slide in animation and the fade in animation both implement this interface. Now we have a way to interface with two different scripts in the same way. We can simply use getComponent IUI animation, and that will get any script which implements the IUI animation interface, and then we just call its play function. Let's continue on the topic of object-oriented programming. If you ever have one class that is a certain subcategory of another class, you may want to consider using inheritance. You can make your class extend another class with a colon, the same way you would implement an interface. This means that all public and protected members of the superclass will be accessible by the subclass. The main advantage of this is you don't have to rewrite code shared by both classes. If for some reason you do want to change the implementation of an inherited method, then you can override it. In my game, I have several types of weapons. For now, there are assault rifles, shotguns, and submachine guns, which all behave a little differently. Even though they are different, the majority of the code for each weapon is the same. So I could either copy and paste the same code into multiple different scripts, obviously not a good idea, have one script with the code for every weapon, which gets messy real fast, or I could have multiple gun classes that inherit from a parent class. That's the best option. In practice, this means all the guns can share the same code for generic functionality like ammo, fire rate, and parsing input. Oh, and what if I want to add melee weapons in the future? All weapons need to respond to input, and all weapons will have a fire rate, so I can put that code into a super class called weapon. Now all guns inherit the weapon code from the weapon class as well as the generic gun code from the gun class. Here's one more trick. If I make the weapon class abstract, then I don't actually have to implement every method. Similar to interfaces, subclasses will have to provide the implementation. Of course, I can no longer instantiate a weapon by itself because the class is incomplete, but that makes sense because I'll never have just a weapon. Here's a less obvious use case for inheritance that also combines a lot of the previous tips. In my game, I have bots and I have players. I want each character to use the exact same movement and gun scripts. Just in one instance, the input will be provided by the player, and in the other instance, the input will be calculated by the AI. I started off by checking if the player was a bot in each script and then getting the input from the corresponding source. But this got really annoying and messy as I added more mechanics. My solution was to make an abstract class called Input Handler. Input Handler has a public method that allows scripts to subscribe to receive input. Now, I have two subclasses of Input Handler, Client Input Handler and Bot Input Handler. These classes send the character input to their subscribers every frame using that character input struct we talked about earlier, although they populate the struct in completely different ways. Because I want to interact with different scripts in the same way, I'm using an interface here called IReceiveInput, which is implemented by every class who wants to receive input. This is a common event listener design pattern. Here's where the magic happens. Inside my player scripts, all I have to do is get an input handler component and subscribe to its events. Since the client and bot input handler are both types of input handlers, this code will work whether the character has a bot input script or a client input script attached. For the most part, all the character scripts don't even need to know if the character is a bot or a real player. My weapons have a lot of different stats. I need to reference these stats in several different places, from the weapon scripts to the weapon selection screen. Fortunately, Unity recently released a feature called scriptable objects, which are perfect for bundling data. The main advantage they have over normal classes is you can access them in the inspector without having to attach them to a prefab or object in the scene. To create a scriptable object, just extend Unity's scriptable object class and then add the members you want to be included. Then, in the project, I can create an instance of that scriptable object by going to New, Weapon Stats. Now I can rename it and set all the variables. Here's where things get cool. I can replace all the stat variables in my weapon class with a gun stats class, and then watch this. I can just drag the gun stats object into that field in the inspector, and now this gun script will use all the stats from that scriptable object. But wait, different weapons will use different stats. Lucky for me, scriptable objects can also extend each other, which works exactly as you would expect it to. The shotgun stats object now includes all the variables from the gun stats object. And because of polymorphism, the gun script can use a shotgun stats object the same as it uses a gun stats object. I also use a scriptable object to hold the entire weapon set, which I use in the weapon selection screen. Custom editor tools can range from crazy UI menus to simple scripts that interact with the scene outside of play mode. Even simple tools can massively improve your workflow. I just recently started experimenting with these. If you saw my map creation video, you know that I had to add box colliders throughout the entire scene. The problem is, Unity generates a navigation mesh with the mesh renderers, not the colliders, meaning the navigation mesh didn't match the actual colliders. This caused my bots to get stuck trying to reach places they couldn't. To fix this, I made a script that looped through all the colliders and generated a mesh to match the bounds of the box collider. Then when I wanted to generate the nav mesh, I could enable all the meshes. To add a button in the inspector, follow this template. Make a normal mono behavior that has the function you want to call. Then import Unity Editor and make a new class that extends editor. Add the custom editor tag with type of set to the class you just made. Then override the onInspector GUI function. Then you can add buttons like I did here. I'll close with two super simple tips, which also happen to be the most important ones. First, use a version control software. I use Plastic SCM because that's what Unity provides by default. Most version control software will allow you to push changes to the cloud, which means you'll have a backup of your project at every stage in development. I've lost significant portions of my projects before, and because I wasn't using version control, I had to rewrite everything. It makes no sense to spend so much time working on something and not go through the extra effort to make physical and online backups. As a plus, most version control software also allows you to easily transfer your project files from computer to computer and easily collaborate with others. Finally, refactor often and write code well the first time. Many developers, including myself, write code haphazardly without planning and without preparing for the future, usually under the impression that they'll go back and refactor everything at a later date. Spoiler alert, you won't. The longer you push it back, the more daunting of a task it becomes and the less likely you are to do it. Even when you are prototyping, unless you plan on rebuilding the project from the ground up, you should take extra care with how you program and how your systems interact. Nobody likes to rewrite code that they've already written. As a young, self-taught game developer, I didn't discover these tools and techniques for years. Hopefully this video helped you to skip the learning curve and exposed you to some of the more advanced programming devices that don't get enough attention. If anything was completely new to you, I encourage you to do some more research on your own in order to completely grasp the concept. I know I probably went too fast to fully explain everything. I also didn't provide a one-size-fits-all design pattern.
The data structure that every
Hey there, boys and girls. My name is Kyle. Hey there, boys and girls. My name is Kyle, better known on YouTube as Planecraft, and today we're going to be talking about GPU instancing. As always, if you want to jump around this video, time codes are in the description. And without wasting more time, let's get started. Alright, so the first thing we have to do is actually run some numbers. So I devised a little bit of an experiment to see how great GPU rendering is, if it's actually great at all. Before we get started, let's cover what we'll be running this on. My computer currently has a GeForce GTX 1070. The CPU is running an AMD FX 8350 8-core processor, and I have 16 gigs of RAM installed on a 4K monitor. Now this is important because GPU rendering renders off your GPU, hence the name. So the better the GPU, the better the rendering. If we head over into Unity, we have two empty objects set up, one for CPU and one for GPU. They both have basic spawner scripts. It takes a number of instances, a maximum position for randomly placing the objects, and a prefab. On the GPU side, we have number of objects we want to place, max position, and then we have our mesh and our material. When running the numbers, all I did was enable or disable whatever the game object I was testing at the moment. So now let's actually jump into the numbers. At a whopping 100,000 cubes, the GPU rendering was getting a solid 5 frames a second. Oof, it's not off to a good start. But that is actually pretty good compared to the CPU instanced and non-instanced version. We're getting 3.6 and 3. Now when we jump down to 10,000 instances, you'd think the numbers would change drastically. You think 5 for the GPU and 3 for the non-instanced, you'd think that number would stay the same, but it doesn't. Actually, at 10,000, GPU only gets 37 frames a second, while CPU instance hits 55 and non-instance hits 49. Things continue to get weirder as we drop down even smaller. At 1,000 instances of our cube, GPU is still at 39, while CPU instance is at 46, and CPU non-instanced is at 48. Now I was staring at these numbers for quite a while, really trying to rack my brain about what the fuck was going on. Why are the numbers not going up so much? And why is GPU struggling so hard? And then I realized this was just in Unity. Unity has a pretty taxing engine to run, and when you're actually viewing the stats, it has to run on those calculations as well. So I decided to do the ultimate test and actually do a build of the game, and then run each build several times, testing out GPU, CPU instanced, and CPU non-instanced. These numbers actually tell a different story, and a much better story, if I'm being honest. At 100,000 cubes in build, our GPU is at 15 frames a second. Our CPU instance was at 2, and our CPU non-instance was at 4. That means we gained 10 frames a second for our GPU. Our unsung hero is looking pretty good right now. When we drop down to 10,000 cubes, in editor, GPU was 37 frames a second. In build, it went up to 40. While both CPU instanced and non-instanced went from 55 and 49 respectively to 30 and 30. And all the way down at 1,000 instances, GPU went from 39 to 57, while CPUs only got a small boost from 46 and 48 to 50 and 50. Overall across the board, when we look at the numbers, we can see that GPU instancing within the build always beats out of everything else, even if it doesn't look like it's that great when you're just running it in the editor. So now that we know what we need to do, how the fuck do we actually use this thing? And trust me, that's a great question to ask because I spent about 12 hours over the course of 7 days trying to figure out how GPU instancing works. The docs and the wiki are not that great. They show you how to actually set up a surface,
does my stream by any chance
a
still say that
subsurface
I'm
shader
playing
for
Halo
it,
Infinite?
but they don't show you how to generate the stuff
I
in
just realized I don't think I
scripts. And
fixed
there are
that
some
or
tutorials
changed it,
online. I found
rather.
one tutorial where the guy
That'd be so
briefly
funny if it
covers
was.
it. He doesn't really show too much of the code. He just kind of talks about the idea
Oh, no, it
of
doesn't.
it.
Alright,
I
that's
found another tutorial where someone gave off some code
I was
snippets,
just being
but those
paranoid.
code snippets were outdated. So after slaving away, tearing my hair out to figure out how this worked, I finally have a tutorial for you guys. I'm going to be in Unity 5.6.3, which is important because some of the stuff isn't going to be available until 5.6.3. For example, on a material, if you want to enable GPU instancing, you need at least 5.6 and up. If you're on 5.5, you can still create your own instance shader by right-clicking, going to Create, shader, and then they should have an instance version of the standard subsurface shader. If not, you can always try going to the wiki, grabbing the subsurface instance script, creating a new subsurface shader, and then pasting in the script and seeing if it works. Again, I don't know. I know I switched over to 5.6 and I've been loving it. Now that's all out of the way, let's move over to phase 2 and actually writing the code. Alright, so in Unity, the first thing we need to do is to actually set up our material. It's pretty easy in 5.6.3 or 5.6 and above. All we're going to do is to create a material. We're going to call it instanced mat. For my example, I don't need specular highlight or reflector, so I'm turning those off. And then we just check the little box that says enable GPU instancing. Some people would make you believe it's actually that easy, but they're wrong. Yes, it does help with the examples that I showed. However, if you actually adjust the code to spawn things differently, you can actually get a much better result. And that's what we're going to cover next. Let's create an empty object. I'm just going to call it GPU. Make sure it's at 000, and I'm going to right click and create a new script. I'm going to call this spawner. Once it's created, I'll drag it onto our GPU, the component section, and I'll double click the script in order to open
happy
Visual
you're here
Studio.
too. Hello.
Alright, once here, let's get our public stuff out of the way. We're going to need 3 public things. First off, we need a public int called instances. Next up, we need a public vector3 called max position. I'm going to call mine max POS. Then we need a public mesh called object mesh. Public material called object material. So in the order of keeping things simple at first, let's actually jump back into Unity and update our script. For instances, I'm going to pass in 10,000. For our position, I want maximum of 200, 200, and 200. For our mesh, we can actually click this little circle, whatever basic shape we want. I want a cube. And for material, we just drag in our material. Back in our script, things are going to start getting a little complicated, but it's really not too hard if you just follow along. I'm going to start with the easier functions first. In update, we want to render our batches. We'll cover our batches pretty soon. For that, we need a private void, which means it returns nothing, and we want render batches. Alright, within here, we need a for each loop, which means it's going to loop through for each time something is true. So we want var batch in batches. Now it's going to complain that we don't have batches, but that's fine. We'll do that later. Now in here is where we actually create, and by create I mean draw our instance of the cube or whatever shape we're passing in. So here we want to call it graphics.draw mesh instance, and then the parameters we need to pass in our object mesh. We need to pass in any submesh indexes, so I pass in 0. Our material, which is object mat, and then it needs a list of matrices to run through. Now these things actually seem pretty scary at first. I know I was confused on what they did and why they worked and how to work with them, but it's actually not that bad. Basically, all it's doing is it's storing all the important information. You can pretty much think of in Unity your transform as one of these. You can store your position, your rotation, and your scale. So not only are you storing these 3 values, but you're then storing these values to X, Y, and Z. You can store a ton of information. They're actually pretty cool. But for now, all we need to know is we want batch.select, and within these parentheses we want A, create an arrow, A.matrix, go outside this one, we got toList. Basically what we're doing here is we're going to take our batch and we're going to convert it over to a list that it can actually work with our draw instance mesh. In order to get rid of this annoying squiggly line in our batches, we're going to have to create our list of batches. Now I hope you guys really like list because we're about to put list in list. Yeah, I know, crazy, right? What we need is a private list, and that list is going to be made up of a list of an object called object data. We're going to call this batches, and we're going to create a new list. Now it's going to say, what the fuck is object data? That's fine. Let's make that. Above our entire class, we're actually going to create a new class. We write public class, and then we want object data. Now within here, we can declare some public stuff. We want a public vector3 called position. I'm going to call mine POS. We need a public vector3 called scale, and we need a public quaternion. And if you don't know what quaternion is, basically rotations within Unity, and I'm going to call that ROT. Now we need a public matrix 4x4. I'm going to call it matrix. Within that, we're going to set a get. Basically, it means that we can call matrix, and it means we can get the value, but we can't set it from inside another class. It's actually a pretty cool way to protect the stuff that you're working with, so that other classes can't fuck with it. And what we want to do with the get is we need to return our matrix 4x4 dot trs transform rotation scale. And we're going to pass back our position, our rotation, and our scale. Now select's going to start having an issue with this, and that's because we're not using some of the namespaces. So we need to pull in using system.linq. Just close that off and we're good to go. So what we have going on is we have our object data, and this is what we're going to be spawning. We need to be able to track some of these variants if we want to actually manipulate them over time. We won't be doing that in this tutorial, but I will be covering it soon. We have a list of lists called batches, and then we have our render batches, which loops through all our batches and renders it. Now before we go any farther, I'll kind of explain why we have to do what we're doing right now. Basically, there is a limitation to graphics.draw instance meshed. You can't draw over 1024 objects. And because of the limitation, if we want to draw like I was doing 100,000 objects, you have to render everything in batches. So I had to create a system in which we batch up all the objects we create to sections of 1,000. It stores these batches in a list of lists called batches, and then we loop through that list, and then we render everything out. Makes a little bit more sense once we have the rest of the scripts. I guess we'll just move on to the start script. Here what we're going to do is we're going to set an int called batch index num. I'm going to set that equal to 0. Then we need to create a new list, and this is going to be a list of object data. I'm going to call this current batch, or CURR batch. So our batch index number will track us looping through the indexing. Will track us looping through our for loop that we're about to create, and our list cloud data of current batch is going to be our current batch list, and when we're done, we're going to inject that into our overall batches list, and we're going to reset this list back to nothing so we can continue adding more objects to it. So we need a for loop, so we want for int I equals 0, while I is less than instances, we want I++. Now within here, we're going to run a new function that we'll have to create called add cube. I'm going to call mine add object, and it's going to need two things. It's going to need our current batch and our I. We also want to make sure our batch number goes up, so we want batch index number ++, and then we will need to check, is our batch number out of line? So is it past the maximum? So if batch number index is greater than or equal to 1,000, we need to do batches.add. We're going to add in our current batch, and then we're going to do current batch. Current batch is going to equal build new batch function. We'll write that in a second as well. Before we forget, we should also probably set our batch number to be 0 again. So just because it's a little bit easier, let's actually cover our build new batch first. So we want a private, and this time it won't be void because we're actually returning something. What are we returning? We're returning a list of object data, and this is called build new batch. All we're going to do in here is just return a new list of object data, and that satisfies that. Now let's set up our add object script. This one will be private and void. So there's two things we have to do in here. One is actually add our object to the current batch, and the other is to set its random position. Luckily, its random position is actually pretty easy to set. All we're going to do is create a new vector3, and I'm just going to pass in a bunch of random.ranges between the max POS x and the negative of the mass POS x. Once we have our position, we can actually add our object. To do that, we just want current batch.add, and we're going to pass in our new object, and we need a position, new vector3 at whatever scale we want, and our quaternion. However, this is giving some errors. And why is that? Well, because we don't actually have a way to create these objects. We don't have a public function that we can call to actually set this stuff. So what we're going to do below all this is we're going to create a public function with the same name as the class name. So object data. Now this is going to take some stuff. First off, we want to take a vector3, we're going to call it POS. We need to take a vector3 called scale, and we need a quaternion, and that's going to be called ROT. Now inside the function, we need this.POS equals POS. This.scale equals scale. And you probably guessed it, this.ROT equals ROT. Now we need to make sure with our function we're actually pulling in a list of object data called current batch and an int called I. Now we're not actually using I for anything, but it's pretty useful if you want to modify the position based on the loop number. So if you want to draw straight lines or do some other testing, you need that number if you want to modify any of this based on what loop or what object it is in your loop of instances. Alright, with all this done, we should be good to go. We head back in Unity, everything's looking pretty good. Let's click play and see what happens. And there we have it. We check out our stats. You can see it's not too great. We're hovering about 40 frames a second, but there's 10,000 instance cubes spawning within a 200 by 200 by 200 cube. These numbers will only go up once you actually build it and run it, but overall it's not too terrible. Based on the endless testing that I did beforehand, you can tell that this is probably one of your best bets if you have to spawn a lot of stuff. However, before I leave you, there is a drawback to this. The object mesh has to be the same mesh. You don't have to use one of these basic primitive objects, but the mesh you're using does have to be the same across all of it. And I believe you're limited to one material. At least I haven't found any examples online of people using multiple materials and actually getting them work without writing custom shaders to adjust specific colors of specific vertex. So this might not be a catch-all for you if you're generating a lot of different objects. It might be great to do this in small batches and you can implement that yourself and test it. But if you just want to generate one of the same object over and over again, this is where the powerhouse of the GPU instancing comes in. And well, why is that? Well, basically in a normal game, your CPU has to process all the cubes in the scene and then pass those children over to the GPU, and the GPU takes in all that information and then renders out your cube. But in GPU batching, we process all that stuff when we generate our cubes, and then it says, hey, all these things are similar objects within this batch, so you can actually just reuse the data we've given you, minus some of the stuff like the rotation, the scale, and the positioning. But the materials and the model are going to be exactly the same, and it really cuts down on the render time, and it really cuts down on how much your computer has to work. And so by being able to reuse that data, it's actually able to spit out quite a bit of stuff. If you actually want to go to it, you can go to Window, Frame Debugger, enable it, and you can click through some of this stuff. And you can kind of see cubes spawning in as it's running through the different draw calls and the different batches. Pretty cool stuff. I found it pretty helpful. I'm looking forward to using it in new tutorials along with other optimization tips that I have coming up in order to try to make your Unity games not run like dog shit. As always, my name is Kyle. You just learned something cool today, and I'll see you next time.
Open eye. Feel the
That's really
waves
loud,
cut
Kyle.
through
Oh my
me.
god. That was a very loud outro. There we go. Alright. Fuck it, let's watch an Ace Rolla video. Why not?
Can't get enough of the grass, huh? Can't get enough of the grass, huh? Me neither. I've been on this shit for, a little over a month straight now. If you haven't already, please watch the predecessor to this video, as most of this won't make any sense otherwise. But
I've
don't
already
worry,
seen it.
I'll wait.
Oh, he's so nice.
Alright, that's long enough. So where did we leave off? Well, we generated all of these grass positions, and then we drew 3 squares at each position, and then we animated it. It looked decent at the right angles, but it had a major problem. If you look down on it from above, it's clearly just some squares. You may have also said to yourself, Ace Rolla, this looks absolutely nothing like Game of the Year 2017, The Legend of Zelda Breath of the Wild. You lied to us. And you're right, if you take a look at these screenshots from the game, you can clearly see that the grass has real geometry and is not just a square. So in this video, I'll be discussing how I obtained this more realistic foliage instead of faking it like we were previously. Just like in the last video, in order to render grass, we need a grass model to use, but Unity unfortunately does not have one for us. This means we need to make one ourselves. That's right. Did you think you could get away with just programming? Sorry, indie developers, you're gonna need to learn some more skills. I've never actually 3D modeled anything myself though, so I started out by lying to Autodesk about my status as a student to gain access to Maya. I went into Maya and I put
Nice.
together a little grass blade model. It could probably be optimized more, but as it stands, it contains 15 vertices, which is plenty for getting a nice animation going. Now that we have a grass blade mesh, the neat thing is that I don't need to do anything new to get it working. All I need to do is replace the quad mesh I was instancing before with this new mesh. We can press play to see our new amazing grass blades, and it looks pretty bad.
Cool.
Without the image texture covering up space, we need to draw a lot more grass blades to make it dense enough. We can just up our values though, and we achieve the desired density. Another issue is that we are no longer relying on a texture to color our grass, so we should probably fix that. All of the coloring is going to be done in our fragment shader, the rendering pipeline stage that controls the final output of a pixel on the screen. I've decided not to use a texture and to parameterize all the colors instead, so I can have fun playing around with it. My grass coloring works like so. I have two colors that form a gradient up the grass blade. Additionally, I have an ambient occlusion color that controls the color of the bottom of the blade, as well as a tip color that additively blends with the top of the blade of the grass. It's pretty simple, but it allows me to do many different color combinations. Here's a few of my favorites.
Pretty.
Outside
Very
of
pretty.
coloring, I also added the ability to scale the grass upwards manually and make it longer or shorter.
Oh, scale
Our
that shit.
grass is looking a little stiff, so we should work out a new animation.
Hell yeah.
The biggest benefit of having real geometry for our grass is that we can have a very nice animation, since each individual blade is simulated. If you recall from the previous video, we did all of our animating in the vertex shader. We could get away with it then, since each mesh only had 4 vertices, but doing all that math with our new grass would be quite costly given the major increase in vertex density. So we will be implementing a new method that involves a texture that scrolls across our grass field and displaces the grass. In order to support this though, we need to expand our compute buffer to hold more data. If you recall from the last video, we are storing all the grass positions in this big array that lives on the GPU. Thankfully, compute buffers can hold any arbitrary data type. If we create a struct that contains both the position of our grass object and its world space UV coordinates, we will now be able to sample this texture that will scroll across our grass. Once again, our animation is going to be trig function based. Let's start with a simple sine wave.
Oh,
I have
wait, so
changed
that
the
was really
grass
funny?
shader to visualize this texture that is overlaid on top of it. As you can see, we have a basic sine wave pattern on top. If we then add the current time step to the sine wave, we will see that the texture scrolls over the grass field and it looks like a flow field. Kinda. Obviously, the sine wave alone isn't going to cut it, so let's put some noise into the mix. By modifying the XY coordinates used in our sine wave, we can produce twists and turns in the texture that are most commonly used to create marble textures that look like so. I used this technique to generate my wind flow field because I thought they kind of looked like what I wanted. The way it works is we add noise to our XY coordinates before running them through the sine wave. The amplitude of the noise will control how twisty it looks, and the frequency will control how quickly the turbulence will fluctuate. After playing around with the amplitude and frequency, my flow field now looks like so as it scrolls across the grass. This, combined with
shit
our
go.
localized
Hell yeah.
variance per grass blade, as discussed in the last video, makes our grass field look like this with the normal coloring.
Pretty. Oh wow. It's very pretty.
Did you really believe it would be that easy?
No.
Did you really
I
think
didn't.
we could just instantiate
Never
millions
is.
of blades of grass and get away with it? If you did, you're about to get an alarming visit from the performance police, pal. I'm gonna keep it real with you guys. I've been lying to you this entire time. The grass in the previous video covered a 300 by 300 meter plane. In order to get the same performance, this new grass is only covering a 32 by 32 meter plane. That's a performance loss of nearly 90%. Even worse, we couldn't even try to cover the original area if we wanted to. The performance would just be too bad. This is simply an absurd amount of grass that we're trying to create. So how do we fix this? Well, with doctorate thesis level algorithms, of course.
Oh, of course. How did that go?
The first step in making our grass work in the real world is with actual GPU frustum culling. As I mentioned in the previous video, since our grass is instanced directly on the GPU, we don't get frustum culling for free. We have to calculate it ourselves, which turns out to be really fucking hard. The reason
Yeah.
this is so hard is because in order for our grass to be instanced, the memory buffer we use to sample grass positions must be contiguous in memory. That is, there's no gaps in the buffer, so we can't simply just mark grass positions as outside the camera view and move on with our day. The actual solution is much more sinister. The general solution here is called scan
Sinister?
and compact.
Such a
What we're going to do is we're going to
powerful
take our
word
grass
used to
position
describe that.
buffer and vote on the positions to determine which grass blades are in view of the camera. Then we're going to scan the vote buffer to calculate the new indices of the visible grass blades. Then we're going to compact the visible positions into a new buffer using the indices calculated above. In greater detail, with an example, take this buffer of 5 grass positions. First, we vote on the positions and mark which ones are visible with a 1 and the others with a 0. Then we scan the vote buffer. The specific term for this is prefix sum scan, meaning each element of the array becomes the sum of the previous elements in the array. This is the really complicated part that I wish I could explain in greater detail, but I'm simply not skilled enough to do so. Please refer to the links in the description that I used to learn the algorithm. Lastly, we use the scan buffer to copy data from the positions buffer into a new buffer using the positions calculated from before. The result is a buffer of grass positions that is contiguous in memory and only includes grass that is in view. This process executes every single frame to calculate which grass is in view and updates the buffers accordingly. But does it actually work? Yeah, it does. With the camera placed in the center of the plane, we see a nearly 50% performance increase, and when the camera faces away from the grass, we see essentially no change in performance from the max FPS that Unity 2022 displays. But does it scale? No, unfortunately not. We still need to do a lot more work to get this grass to cover the same amount of area as the grass in the previous video. This is a problem that I am still actively trying to solve, since I learned how GPU culling works about a few days ago. Overall, am I happy with the visuals of this grass? Absolutely. I think it looks very, very nice. If you liked it, or have any criticisms, I'd love to hear about it in the comments. There's still a lot I'd like to do with the visuals, but this was the best I could do given my 2-week time
Is it replacing every
constraints.
single fucking...
In my next video, I'll be going over the full optimization pipeline and getting this grass to cover as large of an area as I want while still being highly performant.
Oh, because
I'd
that's a
appreciate
texture,
it
it's
if
not a
you
material.
subscribe
I'm
so
fucking
you know when
stupid.
that
God
video
damn it.
comes out. But until then, I hope you have a
There we
great
go.
rest of your day, and
Here's
I'll
what
see
I
you
like.
next time.
Very pretty Acerola. Very nice.
Previously on the Grass Diaries. Acerola, this looks absolutely nothing like Game of the Year 2017, The Legend of Zelda Breath of the Wild. You lied to us. I went into Maya and I put together a little grass blade model. Without the image texture covering up space, we need to draw a lot more grass blades to make it dense enough. We can just up our values though, and we achieve the desired density. Did you really believe it would be that easy? In order to get the same performance, this new grass is only covering a 32 by 32 meter plane. So how do we fix this? Well, with doctorate thesis level algorithms, of course. The result is a buffer of grass positions that is contiguous in memory and only includes grass that is in view. This process executes every single frame to calculate which grass is in view and updates the buffers accordingly. Hello everyone, and welcome back to a new video, and what I hope is the last video on this topic. Our goal today is getting the grass we created in the last video to cover any area we want while still being highly performant. But as it stands, we have two main problems. Our GPU culling only works on up to 262,000 grass blades, which is not nearly enough to cover any area we want. Additionally, we use the same grass blade model regardless of view distance, even though grass far away is barely visible. But what if I told you we could solve both of these problems at the same time? Take a look at this square with an area of 300 meters squared, the same as our target area. While we could have a single buffer of grass cover this up, it would not be nearly dense enough to look like a complete field. But what if we had multiple buffers of grass? We could divide up this square evenly and have one buffer of grass positions for each piece. We then run our culling algorithm on each buffer, and the result is an area of grass as large as we could ever want. This method of data division is known as chunking, a concept mostly everyone should be familiar with due to the massive success of Minecraft, a game in which the chunks are extremely obvious. With some changes to position calculation and some tinkering on the code to keep track of multiple buffers, our grass field now looks like so. Well, it's the exact same, which is great. If we visualize the chunks of grass in our shader, we can see that the field is properly divided into any number of chunks. In this case, it is 5 per axis, for a total of 25. We are now able to expand our grass field to the area of the original billboard grass, and we find that it actually works quite well. I get an average of about 64 FPS at full resolution, but this fluctuates depending on the position of the camera. There's still a lot more we can do, so let's move on to implementing level of detail. In order for level of detail to work, we need a lower poly grass blade model. I went into Maya and modified the model we were using to be just a single triangle. I also took the time to optimize the higher detail model. I reduced